Dear students, welcome back. Today we will discuss about the Smith chart in transmission line problems. Okay, this is a Smith chart. We will see how to construct the Smith chart and its applications today. Smith chart. The Smith chart is a graphical tool used in transmission line and microwave engineering to solve problems related to impedance, reflection coefficient, and impedance matching. Okay, the definition of Smith chart. Smith chart is a graphical representation of the complex reflection coefficient plane that allows conversion between impedance, admittance, reflection coefficient, VSWR. It simplifies calculations involving transmission lines and impedance matching. We start with the reflection coefficient. The reflection coefficient is given by ZL minus Z0 divided by ZL plus Z0. To simplify normalizing the load impedance, Z is equal to ZL by Z0. Here Z is a normalized load impedance, where R is the normalized resistance and X is the normalized reactance. Therefore, the reflection coefficient is equal to Z minus 1 divided by Z plus 1. And substituting Z is equal to R plus Jx in the reflection coefficient equation, then now the reflection coefficient is equal to R plus Jx minus 1 divided by R plus Jx plus 1. Let us assume the reflection coefficient is equal to U plus Jv, where U is the real part and V is the imaginary part. See here, we are converting this graph from the jet plane. The right half of the jet plane is uh, is is mapped to the interior unit circle in the reflection coefficient plane. By multiplying the complex conjugate on the numerator and denominator, the reflection coefficient equation will becomes uh, of substituting the values here, you will get the real part and the imaginary part, U and V. The equation of a constant resistance circles, keeping R constant and eliminating X, you will get a, a equation for a circle with a center R by 1 plus R comma 0 with a radius 1 by 1 plus R. These are the constant resistance circles of the Smith chart. Now, if you plot these constant resistance circles on a reflection coefficient plane, all points on the circles have the constant real part of the impedance, that is resistance. This is the normalized resistance circles. Similarly, for constant reactance circles, by keeping the X constant and eliminating the R, here we will get these are the this is the equation we will get. This is also it represents a constant reactance circle with center 1 comma 1 by X with radius 1 by mod X. These are the constant reactance circles. We can plot these circles in a positive reactance and negative reactance circles. Positive reactance indicates the inductance and the negative reactance circle indicates the capacitance. All the points on the unit circle have the constant imaginary part of the impedance, that is the reactance. It is a normalized, these are called normalized reactance circles. With the positive reactance, it indicates the inductive, and with negative reactance indicates the capacitance. By superimposing the two circles, constant resistance circles and constant reactance circles, this is called the Smith chart. Because the Smith chart construction, the Smith chart is obtained by plotting constant resistance circles and constant reactance circles inside a unit circle representing the modulus of the reflection coefficient is always less than or equal to 1. The key points on the Smith chart: at the center, Z is equal to Z0, it's a matched load. Right side edge, it is the open circuit, and left edge is short circuit. Upper half is inductive resistance, inductive reactance, and lower half is capacitive reactance. Impedance and admittance on the Smith chart. This section explains how the Smith chart is used to find impedance, admittance, and impedance transformation along a transmission line. First one is normalized impedance. Before plotting on the Smith chart, impedance must be normalized. Here, this is a normalized load impedance. Z is equal to ZL by Z0, where Z is the load impedance, Z0 is the characteristic impedance. Let Z is equal to R plus Jx, where R is the normalized resistance and X is the normalized reactance. Plotting impedance on Smith chart, there are two steps are there. First one is normalize the load impedance, ZL is equal to ZL by Z0. Locate the resistance circle R, locate the reactance circles X. The intersection gives the load point on the Smith chart. Next, third one is finding the admittance. Admittance is Y is equal to 1 by Z. This is the normalized admittance, where Y is equal to Y by Y0, where Y0 is equal to 1 by Z0. If Z is equal to R plus Jx, then Y is equal to G plus JB. G is the conductance and B is the susceptance. Okay, we can solve transmission line problems without using the Smith chart. Later we'll see using the Smith chart also we can solve these problems very with less complexity. Let us consider we have a problem here. A load impedance ZL is equal to 60 plus J 20 ohms is connected to a lossy transmission line whose characteristic impedance Z0 is given here. Now we have to determine the reflection coefficient at the load and the voltage standing wave ratio at the load. Okay. Here the given load impedance, characteristic impedance, and we want to find out the reflection coefficient and VSWR. For calculating the characteristic impedance, Z0 is a complex value. By simplifying this equation, we'll get this is the Z0 converting the rectangular form. Converting to rectangular form, we'll get like this. By simplifying these complex values and taking the root, we'll get this expression. This is the Z0 value. Similarly, the reflection coefficient is given by ZL minus Z0 by ZL plus Z0. Okay, by substituting here also, we are also getting a complex numerator and denominator as a complex value. After simplification, we will get another complex value with a magnitude 0.220. Now coming to the VSWR value, the voltage standing wave ratio is equal to 1 plus magnitude of the reflection coefficient divided 1 minus magnitude of the reflection coefficient. By substituting this, we will get S is equal to 1.56. Dear students, please go through these two problems and try to solve here and find out the deflection coefficient and VSWR for these two problems.